Recently, the UK government set targets in the next few decades to try and completely decarbonise our electricity grid. To do that is challenging, and there are lots of energy forms that can help us do this, many of which you will be familiar with, such as wind energy and solar energy. But one you may not be so familiar with is nuclear energy. We've used nuclear energy in the UK for well over 50 years. And nuclear energy can run 24/7, so it can help when the wind is not blowing or the sun is not shining in making our grid stable, which is really important for it to work properly. So what is nuclear energy? Well, nuclear energy comes in two forms. One is called nuclear fission, which is splitting big heavy atoms, and the other is called nuclear fusion, which is what happens in our sun and brings life to the Earth. So in terms of nuclear fission, what we do is we take a very heavy atom and we bombard it with neutrons, and it splits into two smaller atoms, giving out energy and neutrons. In nuclear fusion, we're fusing very light elements such as hydrogen together. That technology is not something that we as humans have managed to harness yet, but we're working very hard on the technology to do so right now. Now, one of the downsides is that the byproducts of those nuclear reactions is that they throw out neutrons. They're important for the reactions themselves, but nonetheless, neutrons can interact with matter. And that's where I do research. So neutrons flying out can interact with the nucleus of atoms. They don't interact because they're not charged particles with the shells of electrons, but just occasionally they may interact with the nucleus of an atom. When they do that, they knock the atom out of its lattice site, and they can create these things at the atomic level called cascades. And these cascades create all sorts of defects. You can imagine atoms leaving their atomic sites and leaving holes behind. And these sort of defects really affect the material's properties, and so they're something that we need to understand to really harness the power of nuclear energy. In nuclear power, we need materials for a range of different things. The power stations themselves are usually made out of high-strength steels, often need to be very resistant to high temperatures, because the higher the temperature we can get to, the more efficient the power station is. But also, as I've mentioned, they need to be surprisingly resilient to radiation damage. So these atoms that are being knocked out of their lattice sites all of the time, they change the crystalline structure of the steels or other alloys, some of which are very specific to the nuclear industry, such as zirconium alloys, which I do a lot of research on. And equally, even in nuclear waste. So when we have material which has become radioactive from a power station and we need to deal with that, we can take it out and we can actually encapsulate that material in other types of materials, such as glasses and ceramics. And they need to be able to absorb that radiation damage, in many cases over thousands of years. And so we need to do research to understand how they are tolerant to radiation damage over those sorts of lengths of timescales. The research we do here in the Department of Materials allows us to help the nuclear industry with some of their problems. So it allows them to predict when the end of a power station life is, and to produce new materials that may be more radiation tolerant. And that's what we're doing for new nuclear power in terms of Generation 4 reactors for nuclear fission, and for programs like the STEP nuclear fusion program at Culham.
My name is Aaron Chote, and I am a PhD student here in the Centre for Nuclear Engineering. My project is to look at a specific nuclear alloy currently used in one of our nuclear reactors here in the UK. The aim of my project is to use an atom probe, an instrument recently acquired by Imperial, to take a sample that is often very small, we're talking on the nanometer scale, and then subjecting it to an electric field, which then pulls the sample apart atom by atom and then reconstructs it on the other side using the software. This software then allows us to look into the elements that are present in our sample, specifically looking at their relative abundance and what type of element is present. And then it also allows us to look at how these elements form and where do they move in the sample, i.e. do they move to certain features, do they only appear in certain areas? And then that allows us to kind of put it all together and understand what kind of properties are promoted due to those elements being present. And then that, in turn, allows us to have a better understanding of the materials currently used in our nuclear reactors today.